Continuing from where we left off in the last video, when using technology for hypothesis tests of proportions, we must usually enter the sample size n and the number of successes x. But in real applications, the sample proportion p hat is often given instead of x. The number of successes x can be found by evaluating x equals n p hat, as shown in the example on the next slide. Note that these results must be rounded to the nearest whole number. A study of sleepwalking or nocturnal wandering was conducted, including information that 29.2% of 19,136 American adults have sleepwalked. What is the actual number of adults who have sleepwalked? The number of adults who have sleepwalked is 29.2% of 19,136, or 0.292 times 19,136, which is equal to 5,587.712. But the result must be a whole number. We cannot have 71.2% of an adult. It would be messy. So we round the product to the nearest whole number of 5,588. Caution: when conducting hypothesis tests of claims about proportions, slightly different results can be obtained when calculating the test statistic using a given sample proportion instead of using a rounded value of x found by using x equals n times p hat. Using the same sleepwalking data from the previous example, n equals 19,136 and p hat equals 29.2%, would a reporter be justified in stating that fewer than 30% of adults have sleepwalked? Let's use a 0.05 significance level to test the claim that for the adult population, the proportion of those who have sleepwalked is less than 0.30. Requirement check. 1, the sample is a simple random sample. 2, there is a fixed number of independent trials, 19,136, with 2 categories: a subject has sleepwalked or has not. 3, the requirement of NP is greater than or equal to 5 and NQ is greater than or equal to 5 are both satisfied, with n equals 19,136 and p equals 0.30. The 3 requirements are all satisfied. Step 1, the original claim is expressed in symbolic form as p is less than 0.30. Step 2, the opposite of the original claim is p is greater than or equal to 0.30. Step 3, because p is less than 0.30 does not contain equality, it becomes H1. We get H naught is p is equal to 0.30, the null hypothesis, and H1 is p is less than 0.30, the alternative hypothesis and original claim. Step 4, the significance level is alpha equals 0.05. Step 5, because the claim involves the proportion p, the statistic relevant to this test is the sample proportion p hat, and the sampling distribution of sample proportions can be approximated by the normal distribution. Step 6, if using technology, the test statistic and p-value will be provided. See the StatCrunch results below showing that the test statistic is z equals negative 2.41 when rounded, and the p-value is 0.08. If technology is not available, proceed as follows to conduct the hypothesis test. The test statistic z equals negative 2.41 is calculated as follows. Z equals p hat minus p over the square root of p times q divided by n, which is equal to 5,588 divided by 19,136 minus 0.30 divided by the square root of 0.30 times 0.70 divided by 19,136, which is equal to negative 2.41. For this left-tailed test, the p-value is the area to the left of the test statistic. Using table A2, we see that the area to the left of z equals negative 2.41 is 0.0080. So the p-value is 0.0080. Step 7, because the p-value of 0.0080 is less than or equal to the significance level of 0.05, we reject the null hypothesis. Step 8, because we reject the null hypothesis, we support the alternative hypothesis. We therefore conclude that there is sufficient evidence to support the claim that fewer than 30% of adults have sleepwalked. Instead of using the normal distribution as an approximation to the binomial distribution, we can get exact results by using the binomial probability distribution itself. Binomial probabilities are a real nuisance to calculate manually, but technology makes this approach easy. Also, this exact approach does not require that NP is greater than or equal to 5 and NQ is greater than or equal to 5. So we have a method that applies when that requirement is not satisfied. To test hypotheses using the exact method, find p-values as follows. Identify the sample size n, the number of successes x, and the claimed value of the population proportion p used in the null hypothesis. Then find the p-value by using technology for finding binomial probabilities as follows. In a left-tailed test, the p-value is equal to the probability of x or fewer successes among n trials. And in a right-tailed test, the p-value is equal to the probability of x or more successes among n trials. In a two-tailed test, the p-value is equal to twice the smaller of the preceding left-tailed and right-tailed values. There is no universally accepted method for the two-tailed exact case, so this case can be treated with other different approaches, some of which are quite complex. For example, Minitab uses a likelihood ratio test that is different from the approach described on the previous slide, but still commonly used. In testing a method of gender selection, 10 randomly selected couples are treated with the method. They each have a baby, and 9 of the babies are girls. Use a 0.05 significance level to test the claim that with this method, the probability of a baby being a girl is greater than 0.75. We do our requirement check. The normal approximation method requires that NP is greater than or equal to 5 and NQ is greater than or equal to 5, but NQ equals 10 times 0.25, which is 2.5. So the requirement is violated. The exact method has only the requirements of being a simple random sample and satisfying the conditions for binomial distribution, and those two requirements are satisfied. Here are the null and alternative hypotheses. H0 is P is equal to 0.75. That's our null hypothesis. And H1 is P is less than 0. I think that should be greater than 0.75, which is our alternative hypothesis and original claim. Yes, it should be P is greater than 0.75. I mistyped, sorry. Instead of using the normal distribution, we use technology to find probabilities in a normal distribution with p equals 0.75. Because this is a right-tailed test, the p-value is the probability of 9 or more successes among trials, assuming that p equals 0.75. The Statdisk display on the next slide displays exact probabilities from the binomial distribution. This display shows that the probability of 9 or more successes is 0.2440252 when rounded to 7 decimal places. So the p-value is 0.2440252. The p-value is high, greater than 0.05, so we fail to reject the null hypothesis. There is not sufficient evidence to support the claim that with the gender selection method, the probability of a girl is greater than 0.75. Here is that display. A criticism of the exact method is that it is too conservative in the sense that the actual probability of a type 1 error is always less than or equal to alpha, and it could be much lower than alpha, which is the desired probability of a type 1 error. A simple continuity correction improves the conservative behavior of the exact method with an adjustment to the p-value that is obtained by subtracting from it the value that is 1/2 the binomial probability at the boundary as shown below. This method is easy to apply if technology is available for finding binomial probabilities. Simple continuity correction to the exact method. In the left-tailed test, the p-value is equal to the probability of x or fewer minus 1/2 times the probability of exactly x. The right-tailed test, the p-value is equal to p of x or more minus 1/2 the probability of exactly x. And in the two-tailed test, the p-value is equal to twice the smaller of the preceding left-tailed and right-tailed values.